How are you? And this is another example for the principle of the impulse and momentum. So in this example, just one second, let me get the pointer here. So in this example, we have this is rotating. And then suddenly we're going to apply the brake on it using the L lever here by adding the force P at the point C. Okay, so what's happening is that the contact between the lever and the disk at the point B will cause the friction force that will force the disk to stop rotating. So we can have the analysis of this operation. First, let's read the question. The mass of the disk is 12 kilogram. Angular velocity was 20 radian per second. If the brake ABC is going to be applied such that the magnitude of the force P will vary with the time as shown in this paragraph, in this graph. So, okay, so we can see from 0 to 2, the force will be come to 5 Newton. And after the 2 seconds, we'll continue at 5 seconds. So we need to find the solution to find the value of the P when we're again, sorry, the time required to stop the disk from rotating. So the coefficient of friction between the disk and the brake is given as 0.4. So once again, this is a free body diagram for the lever ABC, A, B, and C. So you can see that at A, we're going to have direction AX and AY, 4 meter upward, then we're going to go 5.5 meters to the 0.4 meter upward, then 0.5 meter to the left, to the right, then 0.5 meter to the right, further to the point C. And at that point, we're going to have the normal force coming from the B and the friction force coming from the B. On the disk itself, it's rotating to the clockwise direction, so the friction force established should be to the left. So this will stop the rotation from going to the clockwise. At the center point at D, we're going to have the mass going downward. We're going to have the reaction dy upward, and we have the dx force to be to the left. The radius is 0.2 meters, right? So we're going to use all these parameters to find a solution, to find what will be the time required to stop the disk. So we start with showing you the general solution I've given to you, the free body diagram of the brake disk to be drawn first. And for the brake, the sigma or the moment around the point is equal to 0 to find the value of the reaction force at B in terms of P. Then using this result for the disk, we are going to do the equation for the HD1 is equal to sigma or the moment around the point D with the function of time is going to be equal to the HD2. We're going to find the equation that tell me that the change in the time from 0 to t for the integration for the force P as its function of time is going to be equal to 20.40. And by solving, we can find that the time is going to be equal to 5 seconds. So we're going to work on that and see how we're going to reach the same results in my solution. So first, we are going to have the two bodies. This undergoes rotation about the fixed axis through the point D, and the brake is going to be in a static. So the P is a function of time, so the integral is going to be expected. For the free body diagram for the disk, it was rotating with having the I omega first, okay? And then we're going to add the brake, and we're going to have the forces to be the integration for the dx to dt to the left, the reaction force to the y direction upward, the weight going downward, the friction force to the left, and we're going to have the normal force coming from the lever pointing downward. On the other side, we're going to have the IO omega 2. So this is the HD1, this is the HD2, this is the moment we're going to have around the point D. For the lever, we're going to have the A, the B, and the C. I can do the moment around the point A here, and we're going to have this force, okay, multiplied by that distance. That's the moment 1. The moment 2 is going to be this force multiplied by that height. And finally, the P force multiplied by the distance here. We know that the FB is equal to the mu multiplied by the MB. And thus we can find the value of the P as a function of the MB. So the known is that the mass is equal to 12 kilograms. The omega 1 is minus 20 radian per second. It's minus because it's going to the clockwise direction. The omega 2 is 0 because it's going to be stopped at the end. The coefficient of friction is 0.2, and the unknown is going to be the MB and the delta T, and we need to find that. Of course, the P is also unknown at this stage. So we will continue with the solution. Okay, so the equation we're going to use first for the MB on the ABC, we're going to have it as a function of the P by making the moments around the point A. Then for the minus delta T, we're going to use the equation for the impulse to get the value for the time. So again, we start with the ABC. The alpha is equal to 0 because ABC is in static. And we start the moment around the point A, which is going to be equal to the IABC multiplied by the alpha. The alpha is 0, so the sigma of the moment around the point A is going to be equal to 0. So now let's see how we are going to get the moment once again around the point A. The MB multiplied by the 0.5, the FB multiplied by 0.4, and the P multiplied by 1. Now given to this sign, the MB going to take you to the counterclockwise, so this will be positive. Both the FB and the P is going to take you to the clockwise direction, so they're going to be negative. If we're going to write down the equation, it's going to look like that. So the sum of those should be equal to 0. Substitute the MB, FB as mu multiplied by the MB. The P is a P. Here we have 1 meter. The sign here should be negative. Here we're going to have 0.5, and this sign should be negative. Here should be this is 0.4. Here 0.5, and this should be positive. So the equation will be written like that. Now by solving, I can find out that 0.5 minus 0.4 multiplied by 0.4, so it's going to be 0.5 minus 0.16. Okay, and here we're going to have 1. So simply, we're going to find that the MB is equal to the P divided by 0.5 minus 0.16. And we will come to the answer that the MB is equal to 2.941 multiplied by P. Now, once again, just to show you how we got the 2.94, if I'm going to get my calculator here, and let's do the calculations together. So again, we said this is 0.5, but here we're going to have 0.16. So 0.16, which is 0.4 times 0.4. So we're going to change that to a negative value, and then we're going to add it to 0.5. So we're going to get 0.34. Now, when the P going to the other side is going to be changed to be positive, and we have here 0.34 MB. If I can reverse that, we are going to have the 2.9411. Done. So now we proved how we found this value. Now we continue with the solution. That will be the equation number 1, and I'm going to use it where I'm going to do the work for the disk. The first thing we're going to do for the disk, that we know the diameter is equal to 0.2 meters, and we know the mass is 12, so we can calculate the ID value, which is going to be equal to the half of the mass multiplied by the radius square. Okay, so sorry, where's my... Okay. So the ID for the disk can be now calculated, and it's going to be 0.24 kilograms meter square. Now we're going to apply the impulse equation. Okay, so we're going to have the hd1 plus the sigma of the moments integration around the point D as a function of time is going to be equal to the hd2. We said that this will be the rotational or the angular impulse for the calculation, and it's going to be equal to the d multiplied by the omega. So the omega 1 is 20, the omega 2 is 0, so this part is going to be go to 0, and we just need to find what will be the moments around the point D. If we go back to the free body diagram, you'll find that the only moment around the point D, let's go back. Okay, the only moment we're going to have with the force around the point D is going to be equal to the friction force multiplied by the radius. All the other forces are going to have the line of action, which is going to be perpendicular to the point D, directly, okay, except this one. You can see that the distance is present, which is 0.2. So we continue with that. We're going to write down the equation here, and we're going to come out with the answer that this is ID omega 1 is going to be equal to 0.24 multiplied by minus 20. This one is 0. Now we come to this point. The friction force is equal to the coefficient of friction multiplied by the MB and multiplied by 0.2, which is the radius, to the delta T. Okay, so this will be the integration I'm going to have. Now rearrange this equation. The 0.4 multiplied by 0.2, this will be 0.8. And, 0.4 multiplied by 0.2 is going to be 0.08. And here we have 0.24 multiplied by 20. Well, let's use calculator. I don't have to use my skills in the calculations. So once again, the 0.4 multiplied by 0.2 will be 0.08 MB dt here. Okay, and on this side, we're going to have the 0.24 multiplied by 20. And it's going to be 4.8. So now we have here 0.08 MB dt, and here we have 4.8. So I'm going to take this value to the other side. It's going to be positive. Then I'm going to divide the 4.8 by 0.08. This will give me 60. Now, that's mean the integration of the MB as a function of time from 0 to delta t is equal to 60. But I do have the value for the p, as the value for the n, as a function of the p, which was this equation. So if I go to multiply the value I just got here, okay, I'm going to divide it by the 2.941. I will get the value of 20.4. 20.4. Okay, so I'll continue with the solution as normal, but I'll just show you how we got these figures. So now we continue with that. We said that we did the calculation, and then we are going to end up with finding that the integration of the p dt from 0 to delta t is equal to 20.4. Now we know where we got the 20.4, right? Okay, so done. We got that. We go back now to the graph that we have. So this value, the change in this value is going to be equal to the area under this curve. Let me use the pen here. Okay, so this will be the area under that curve. The distance from here to here is going to be equal to the delta t. Okay, the delta t. So you can see that this area is going to be equal to the area of this triangle shape plus the area of this rectangular shape. So for the area here, it's going to be 2 multiplied by 5 divided by 2. Half of the base multiplied by the height. And the area here is going to be equal to 5 multiplied by the t minus 2 seconds, which we don't know how much. So this is the area. That's total is going to be equal to 20.4 that we got from this equation, because that represents the area of the curve. Now we can solve for that. Okay, so the 20.4 minus the 2.5 times 2.5 divided by 5 plus 2 will give me delta 2. Now, again, let's try to do that together, because I know that the student sometimes are going to be lazy to find the answer. So we have the 20.4 that we calculated earlier. And again, to subtract from that, the 2 times 5 times 0.5. Okay. And again, to get the value of 15.4. Divide that by 5, which is that 5 here. Okay. And the answer now is going to be equal to 3.082. Now I'm going to add to that 2 seconds, which is this 2 to go to the other side. And the time is going to be equal to 5.08 seconds. And that's the time actually we got in the answer. Okay, so continue with here. So the time is going to be equal to 5.05, which is the correct answer that we have there. Okay, so that's it. That's the solution. It's look hard, but it's not that hard. You only have to think about it. Okay, so that's it. Thank you very much. And we're going to come back to another question.